Welcome to today's colloquium. Let's see, we're having microphone problems. And so can you all hear me? Okay, great. Our speaker today is Albert Stebbins. And let me tell you a little bit about Albert. He was an undergraduate at Cornell. He got his PhD at Berkeley with Joe Silk in the golden days of, what you call it, the golden days of cosmology. That's kind of the dark ages there now. And then he went to CETA, and then he came to Fermilab, and he's been at Fermilab ever since. And Albert is an extremely versatile theorist. So I'm looking at all the papers that he's written, and starting with the ones that are the most cited. Ultralight bosons, we'll come back to that. And that has to do with both the accelerating universe and many ultralight particles that are dark matter. Probably his most important paper is the paper with Arthur Kosowski and Mark Kamiakowski. What a mouthful of authors that was for that paper, that pointed out the importance of BMOs to detecting gravitational waves produced by inflation. In 1996, I'm giving you the dates for a reason. Weak lensing. His early papers, he worked with a string of collaborators that were really, really smart, because they worked on a really, really hard problem, and that was cosmic strings, how they form structure and how they influence the microwave background. And once they figured out how they influence the microwave background, they were able to kill cosmic strings. Because the reason that cosmic strings survived for so long was that no one knew the fingerprint they left on the cosmic microwave background. They didn't think that was the fingerprint that was being seen. 21 centimeters. He was one of the pioneers, cosmology with the Lyman alpha forest. Why did I read you all these things? Because I asked some people about Albert. We all know he's really brilliant. And they said, oh yeah, if you want to know what to do in cosmology today, look at what Albert was working on 20 years ago. So that's why I read you all those dates. He's always ahead of his time. I just want to mention one honor that I'm sure he's got a lot of other honors, but you know, there's not much information on his own website. It's too modest. But the Institut d'Astrophysique in Paris gives out a scientific medal and for scientific achievement, and Albert was awarded that medal in 2014. So now he's going to, you know, tell us what we're going to be doing in 20 years by telling us about fast radio bursts.
Thank you for having me. Kind introduction. So I'm going to tell you about something which you may have read about in the newspapers, and it might be important for all sorts of fields you don't know yet. So in a sense, it's sort of jump on days fast radio bursts go on forever. All sorts of things, and it's hard to tell what would be important.
So I don't want to, you have to eat that microphone.
All right, okay. So fast radio burst, the first time I heard that was in 2013, as I'll talk about later. And let me just describe what it is. It's a non-periodic short burst of radio energy from space. It comes from space is important. It's localized on the sky, presumably it's a point source as far as we can tell. The angular distribution of the bursts appear to be isotropic. It has an anomalously large dispersion measure compared to the galactic, which is that distinction. I'll explain what that means later if you don't know what that means. So typically a galaxy might have 50 or 20 or maybe 100 or 1,000 if you go towards the galactic center. It's a measure of the amount of ionized gas between you and the source. Generally speaking, these have to have a large dispersion measure. It's believed that this extra dispersion is from the intergalactic medium, and from that, since they were first observed, it's been believed they were cosmological. The typical the duration of the burst, once you correct for various plasma effects, is less than a few milliseconds. They're not periodic, meaning they don't have a particular period, and typically they're not repeating, although at least one repeating source has been identified. And that repeating burst should be, it has a localized redshift of 0.2. So they seem to be cosmological. So the origin of these bursts is not known. So I think everything I said here is true. And so you can take with a grain of salt everything else I say. Many explanations have been proposed. So sort of the jump on days, it's been the jump on days of fast radio bursts the past 2 years. So for those of you who missed it, you may have missed it. Because we're going to get a whole bunch of data. So anyways, one reason I'm here is to promote something that I call ultra-fast radio astronomy. And I think there's a lot of uses for it besides fast radio bursts. And what is ultra-fast? Well, I made up that word. Ultra-fast to me is faster than a blink of an eye. According to Wikipedia, a blink of an eye between 0.1 and 0.4 seconds. So anyways, you might think that there isn't such a thing. Most astronomical objects are observed to have nearly constant luminosity on a human time scale. So for example, in quasars, if a quasar varies detectably in 24 hours, that's called micro variability. So a day is a short time scale in astronomy. Astronomical objects at astronomical distance have to be luminous enough to be detected on such a short time scale in order for you to measure their variation. So, in other words, they have to be extremely bright for you to be able to detect ultra-fast variations in an object. And the travel time across an emission region limits its variability. So for something to vary significantly in less than a blink of an eye, it has to be smaller than about 1/10 of a solar radius, which is smaller than a white dwarf. So, of course, there are exceptions to what I've been saying with gamma ray bursts, but for other reasons, due to boosting, relativistic boosting of the gas. But anyways, so you might think, well, it's very unlikely to see such things from the sky, but nevertheless, recently, and even not so recently, we've seen a lot of these sorts of ultra-fast events on the sky. For example, nanosecond timescale variations in radio luminosity has been observed at a source 2 kiloparsecs away, and the fast radio bursts are observed to vary significantly on millisecond timescales and shorter at distances of about a gigaparsec away. And like I said, these are very bright objects. So anyways, bright objects, well, you're probably familiar with some bright objects. One is sort of lightning. Lightning is probably the brightest thing you've ever seen. There's different types of lightning. There's sprite lightning, which is a much more powerful type of lightning. You don't generally see it because it happens above the clouds. There's solar radio bursts. They also can be extremely bright and powerful. And recently, the satellite has observed this lightning from Stebbins. So anyways, all of these things have to do with large-scale coherent electromagnetic fields, accelerating charges, and the emission mechanism can vary for different types of things. But I'll tend to call these sort of phenomena sparks or electromagnetic pulse. Here's sort of a slow motion version of that movie that someone took of this lightning event. And you can see by looking at things with high time resolution that you can see more of the detail, more of what's going on. And a lot of astronomical observations are set up so that they're not really sensitive to very short time scales. For example, a CCD might have an integration time of a few minutes. In some of the radio stuff I'm doing, we sort of bin the data in second time intervals. But if you want to see these things, you really need to look at with high time resolution, make an effort to do that. And I'm going to tell you what you might come up with. So I just want to welcome you to the world of radio transients, something that I wasn't very familiar with until recently. So here is a plot of something, some actual data. You can see, oops, the time, here's the pointer. So the time scale here is years. The units here, I'm not telling you what they are yet. And you can see this, if this radio telescope was more sensitive to this, but if it would have this sensitivity of about 5 times 10 to the 5, it would have seen a few objects, a few bursts of energy every several years. And so you might scratch your head, what is that? Even if you could convince yourself that it wasn't something that goes wrong with your detector after certain years, which is quite likely. If you increase the sensitivity a little bit more, you'd say, well, yeah, if you go dimmer, you see more events. There seems to be some time structure. There's a bunch here, there's a bunch here. It's hard to say. This is from different frequencies. Some are very bright at the low frequency, some are very bright at the high frequency. Something is interesting is going on. You'd have a hard time inferring from this data what exactly this was. And if you go further, this is what you see, more events. You see more significantly this time pattern. So anyways, what is this object? I'm asking God. It's the sun, right? So you can imagine a radio astronomer or some type of astronomy where all they could see was those top points and none of the bottom points. And they have a hard time figuring out what is going on. So here is, so the sun has been observed very regularly for decades. There's the solar cycle. But what you see is that in the radio, the brightness of the sun can increase by factors of 10,000 on minute time scales, and only very, very rarely. So that's sort of an interesting sort of object to try to figure out what it is. And fast radio bursts are like that. So for example, in this Novayama data, this is the brightest event that they discovered since it was turned on in the late 1980s. It's a 7 gigajansky solar flare that lasted more than half an hour. I think somehow the thing turned off for a period there. So the sun increased by a factor of 10 to the 4 for a short period of time. And so that would be disconcerting if it happened in the optical or infrared. But unfortunately, it didn't. But anyways, these events can be very, very hard to find and convince yourself they're real, unless you have a tried and true instrument. Because they're very rare things, and everyone knows that runs instruments that things go wrong every once in a while in ways you don't expect. And I think the usual procedure is to throw that stuff out. Okay, so here's sort of a base space of short time scale radio events. This is sort of derived from a commonly used figure by Keen et al. So anyways, there's a bunch of things. Here's their duration. Notice that the axes here vary by at least 15 orders of magnitude. The duration goes from nanoseconds to days. There's what they call flare stars. There are bursts of radio energy from solar bursts. There are other things up here, which AGNs, X-ray bursts, not to mention. But on the short time scale side, there's pulsars. So that's the main object of study. Most of the study's been in this range. And the inferred luminosity of these radio bursts is about several micro solar luminosities. And if you just looked here, you might have missed these shorter duration events. But recently, because of the search for pulsars, people found this lot of stuff up here. So at the source, so these things may be as bright or less bright than the pulsars, but it turns out they're further away. And that's why they're up here. And so there could, in this limit, the bottom limit here is basically due to your selection effect. You can't see dimmer things. So maybe there are things that fill in this part of the parameter space at cosmological distances we don't know. And then these other phenomena, giant pulses, which are even shorter, which I'll talk about. And here are the nanosecond things that have been observed from a few pulsars, which are fairly bright. And this is all done in about the gigahertz band. So all these things are I mean, this you can see its full glory of range of phenomena because you observe the sun all the time. Pulsars pulse fairly regularly, so you can just point at them and see what's going on. These things took a little bit more searching and some gymnastics on the instrumentation, and this actually required a lot of searching to find it.
Albert, just stay there a second. So your plot here on that y-axis is, I would say, isotropic equivalent.
Right, yes.
Velocity, but what is the new in front of it?
Well, this is a narrow band measurement, so this is gigahertz. So people measure things in Janskys, that's what they report, and then you can multiply times nu to find sort of a unit bandwidth luminosity.
That's bolometric.
What's the bolometric power in the gigahertz band? They might have much more power in some other band. We don't observe them in other bands, so we don't really know.
There's also assuming isotropic, which is huge.
But you know, with something like a nanoshock, simply diffractive argument suggests you have a hard time keeping something that's a meter wavelength, a meter in size. Okay, so let me now go to a brief history of fast radio bursts. This is partly borrowed from Matthew Bale's talk at a very nice meeting they had in Aspen in early February. So anyways, it's an interesting story. The story sort of begins with pulsars. First, I'm going to talk about periodic pulsars. So they were discovered in 1967 using sort of old technology, and they found this repeating radio signal. People increased their technology and their techniques and were able to find, have greater sensitivity to dimmer pulsars and for faster pulsars over time. And finally, using better computers, they were able to get to millisecond pulsars. And so here's sort of the picture of what's this is the cartoon everyone shows you. It's like there's this rotating thing that's constant except for it's rotating. And then you happen to lie in this narrow beam, which happens to pointing towards the Earth some fraction of the time, and that's when you see the flash. And therefore, what you see is sort of indicated by here, and it's all nicely periodic and repeating. From this sort of picture, and we can use this picture to get from observations, this sort of diagram of magnetic fields and periods. Young pulsars, old pulsars that have been spin up, very highly magnetized pulsars, very, very rich phenomenology. But there's another sort of history that goes along with it, which is sort of the history of pulse variation. So giant pulses were detected from the Crab pulsar. What they found was pulses. They were looking for an object in the Crab Nebula because they knew it was a supernova remnant. They thought they'd get remnant star in there that find pulse. And what they found was that it did pulse, but it did pulse periodically. So they found radio pulse. Actually, they found two sources of radio pulses in that area. And so there were large variations. So here's sort of a picture of, here's sort of a real picture of an actual pulsar, what its pulses look like for 100 cycles. But here's the average of this. So this is what you see in a lot of textbooks. And here's what you see in practice. So it's just sort of like the sun thing I was showing you before. There's a lot of variation, and there's very high peaks and not high peaks sometimes, and it's not as regular as you would think. So the pulse, these things that, I don't know exactly what the criteria is, but these giant pulses, occasionally you see things that's like 100 times this or more. And you can look at these things and you find a power law distribution of these giant pulses. And there seems to be, here's one, but it seems to be sort of flattening things from this paper, which had a large sample of giant pulses from the crab pulsar. And so anyways, it's not like a lot of pulsars have regular pulses. They have all sorts of different kinds of pulses that average out to something that seems to be the same from one day to another. But it's a lot of variation. And another thing that was done recently, more recently, was it was predicted that these, so the time scale for these variations is actually limited by the instrumentation. So you see structure on all time scales you can resolve. And it was predicted by Weatherall that there should be nanosecond time scale things. I sort of like a collapse, sort of like a laser-like effect. I'm not sure I actually believe his model actually works, but in 2003 these were actually observed. And that's sort of the shortest time scale people have ever measured variations in a pulsar. And that again was limited by the instrumentation. So here's sort of a picture of the mean pulse of the crab pulsar. So Jessner et al. And Hankins, the guy that discovered these nanosecond structures, what they did was they didn't run the radio telescope the normal way. They hooked up basically a storage oscilloscope to the radio telescope and recorded traces. And so here's the plot of a trace. This is not the same observation. And what they found, the scale here is microseconds, is all this stuff. Very short, very high pulses, very non-Gaussian features, and the different colors represent different polarizations. You can blow up some of that, and so here it goes less than a microsecond across the whole thing. You see even more structures, and close to a nanosecond, close to the resolution given the bandwidth of their detector. And here's a very bright Megajansky burst from the crab pulsar, which is 2.2 kiloparsecs away. So for that brief nanosecond, it was as bright as the sun.
Going back to your eye-blink thing, does this imply that this comes from a size 10 to the minus 9 of a white dwarf?
It comes from a size of a basketball. So this. And I'll give you a reason why it might happen. So the record pulse was 2 megajanskys, and here's sort of a blow up. Look at that. So here more typically you find 10 kilojansky little pulses of several nanosecond time scale. So if you went to higher resolution, I'm not quite sure what you'd find, but you have to also go to higher frequencies because this is 10 gigahertz observation. You want to go to shorter time scale, you have to work at 50 gigahertz or something like that. And anyways, I don't know how feasible that is. So anyways, that's sort of the history of the structure of pulses. And then there's a sort of related history, which is the identification of the Crab Nebula as a supernova remnant. Again, in 1939, this paper I mentioned before said there were no periodicities evident. And that's because there's this huge variation in things. Eventually, Hawk, Disney, and Taylor noticed that there were optical pulsations found that were much more regular from the Crab pulsar. And the radio location in the period where measured by Dick Lovelace, determined by Dick Lovelace in 1969, and found that the radio phase and output phase align no less. So anyways, this fact that the pulses are so irregular, some tend to be very high, led some people, like a guy named Dietz, to look for single pulses. Not look for, usually the technique for finding pulsars is to look for periodic periods. But since things are so variable, sometimes it might be better to look for single pulses, and once you find sources of single pulses, you might look more closely at what Lovelace did. And there was a big payoff with this in 2006, but in this paper by McLaughlin et al., who found a bunch of things which are called RRACs, or rotating radio transients. Those are just regular spinning pulsars like I talked about, but they're much more variable than typical ones. And the best way of finding an RRAC is to look for individual pulses, not for periodicities, because the signal is very far from exactly periodic. And that motivated people at Parkes to look for single pulses in 2007. And that's how fast radio bursts were discovered. So here's the fourth part of my history. So in 2007, the first radio burst was detected near the Large Magellanic Cloud by this program of looking for single pulses. And the Parkes multi-beam data, which is a data set that was used, that had time resolution because it was trying to find millisecond pulsars. So this thing that he found pulsed once and had a very large dispersion measure, and for that reason it wasn't considered the same class of object as an RRAC. They looked for a very long time for a repeat, and it never did repeat. And Lorimer et al. Interpreted the large dispersion measure as an indication that it was an extragalactic source. So that means that for the brightness they measured, it was extremely bright. And basically, people didn't believe them. And it was quite reasonable not to believe them. Because no one else, and people looked in other archival data sets and they couldn't find another one. And the other thing that's hard to believe the Lorimer burst is that the signal to noise was very, very large. And usually you expect when you first find a new phenomenon, it comes at a low signal size. Because they're expected to be much more common. So anyways, this sort of sat in the bookshelf for a while. And a woman named Perks Bolar also looked at the Parkes data for similar high dispersion events. And she did find a class of objects which she called peritons. Peritons are like things. They seem to have something like a high dispersion, but they're in the side lobes of the telescope. They're not up above. So it's a multi-beam detector, and it lighted up more than one beam, but it was localized in the sky. So you're pretty sure that the Lorimer burst was up in the sky. All these things came from the side because it illuminated all the beams equally. And so that really, even threw another wet towel on this fast radio burst phenomenon. So finally, in 2012, again in archival data, Keene et al. Found a fast radio burst. So this one was, the first one was near the LMC, so far from the galactic plane. This was pretty much very close to the galactic plane. It had an excess dispersion above the galaxy model, but not by much. And it sort of raised doubts on the claim by Lorimer that this was an extragalactic phenomenon. It could be that the dispersion measure was due to some other cloud of plasma between us and the source. So the thing that really changed when I got interested in it was partly because of Jeff Peterson telling me about this paper. Basically, in the improved Parkes multi-beam data, the high time resolution SIRV pulsar survey, Thornton et al. Found 4 fast radio bursts with much better data. And this is really when fast radio bursts started to be taken seriously. In 2014, so far all these things have been detected by the Parkes telescope. So maybe there's something wrong with the Parkes telescope. Right? And was something wrong with the Parkes telescope. But Arecibo found one as well, and this is a very famous one because of what they found later, Spittler et al. And so if these two things had happened, this could have really shut down the field. In 2015, Emily Petroff and collaborators really went after the periton phenomenon, and you can read about it. It turns out to be caused by a microwave bump. But anyways, since real fast, or things classified as fast radios were easily distinguished from peritons, that doesn't worry me too much, though people like Street-Kulkarni argued that peritons suggest that you should take all this field with a grain of salt. But anyways, in 2015, some colleagues of mine actually looking at Green Bank telescope data used for 21 centimeter intensity mapping found one. And one reason this is a breakthrough event is that it was found at 800 megahertz. All these other things were found above gigahertz. So it suggests that these things extend to lower frequency. They also were able to measure a large rotation measure. And since 2013, people have been gearing up to find lots of fast radio bursts. And since 2016, the floodgates have been open, lots of things are online, and all sorts of people are finding fast radio bursts. A lot of them haven't been published yet. So that was a watershed event, this Thornton et al. thing. Another watershed event was this Arecibo one, the original Arecibo event I talked about, was found to repeat. So that's a different phenomenology. Some of them seem to repeat. They had with exactly the same dispersion measure and exactly the same position on the sky. And another thing that allowed people to do was to point at that point with the other telescopes and try to localize it better. And it was found that this event had an associated variable radio source, which is believed to be related to this fast radio burst. So the radio source is variable, but not on the millisecond time scale, which defines the fast radio burst. Since that time, using the fact that you sort of knew where it was, and it was repeating, the VLA and also the European VLBI network have localized this to very high accuracy. And I'll tell you a bit more about it. So the likely host galaxy, if you look at where this thing is, it seems to be in a dwarf galaxy at a redshift of 0.2. So another thing that's sort of come online in the past few months is real-time detections of fast radio bursts. So before people looked at archival data and they started getting faster, looking at things as they come off the telescope faster, but now they have a system that will alert you, a gamma ray alert system. And so that's going on. I guess something which I don't think I mentioned is that another thing people are doing is commensal observing or co-observing different telescopes, looking at the same spot at the same time to see if things happen. And if you only have a millisecond, you're not going to be able to turn your telescope toward the fast radio burst when it happens. So you better be looking at the same spot if you're, say, looking for optical emission at the same time. Typically, what people in transient astronomy look for is after the burst. They look at something after the main thing has happened. Here it might be worthwhile to look at the same time. So anyways, that's interesting, but what are these things? So there's been a lot of speculation. So I haven't seen a paper on this, but people all say, well, maybe the military is doing something. Who knows what they do? Will tell us. There was someone, I don't think anyone who wrote out this paper, but this guy, Gilishan, was playing with the idea that he was colliding asteroids. It turns out when things collide together, they produce sparks. It's well known now in the satellite industry that micrometeoroids impacting your satellite will tend to short out your electronics. And the same thing would happen when asteroid hits each other. So there's galactic sources, white dwarf mergers, exploring stars, but now that we've seen that there seems to be something at cosmological distance, maybe you could cross out this thing. Cosmological sources that have been proposed, well, the sort of obvious ones are compact binary coalescence, two neutron stars merging with each other. Another thing that supernova, of course these two things are related to gamma ray bursts, might be the source. There's an interesting idea that neutron star could form, which is spinning too fast to collapse to a black hole, but it sheds some of its energy, and then it collapses to a black hole later. And in the meantime, all the ejecta around it has disappeared to allow the radio source to get out. That's called a blitzar. Recently, someone proposed coalescing charged black holes. There's some exotic explanations, axion mini cluster bose condensation. So these are cataclysmic things that should only happen once. So that doesn't seem to be true of this one thing that's been localized. There's sort of non-cataclysmic things. So basically, I would say that the most likely thing is something to do with neutron stars, magnetars, or pulsar giant pulses, or magnetar flares. That's a non-destructive thing that happens. Other people have proposed that a neutron star near a depleting black hole has a lot of stuff falling towards it, like spark occasionally. An exotic explanation is that these are actually solar sail boosts by extraterrestrials cosmological distances. That was published, roughly published. So that doesn't really, so that's speculation. So let me go through the evidence a bit. Here's the angular distribution. The places that are observed is not uniform in the sky. This is the angular distribution of a bunch of them, not all of them that have been published so far, but most of them on the sky, galactic coordinates. The blue ones are the Parkes one, the red ones are the utmost one, they're the ones that are bigger. There's the Green Bank Telescope and the Arecibo one, which is actually very close to the galactic plane. So the Arecibo one is different, and that's close to the galactic plane, and it repeats. Presumably those things are not related. It's sort of curious. So another thing is the dispersion measure. So the dispersion measure, like I said, is a measure of the amount of ionized gas along the line of sight. It's usually given in units of parsecs per centimeter cubed. And so here's the parameters of the first Lormer burst. So what the dispersion does is it causes the low frequencies to arrive later than the high frequencies. And that's why it's hard to measure things in the radio, is that you have to de-disperse the signal to get the different frequencies to line up. And if you line them up, you get something that looks like this. And this is noisy data from the Lormer bursts. They use 1 bit AP converter. But anyways, you can measure the dispersion, and here's a measure of the dispersion over a model of the dispersion to the edge of the galaxy in the different directions of the different things. The red dots are pulsars, and the black diamonds are fast radio bursts, and the squares are from the LMC and the SMC. So as you'd expect, the LMC and SMC have a higher dispersion measure than that, just so the galaxy, but so do the fast radio bursts. And they can have orders of magnitude more dispersion than you'd expect from the galaxy. Another interesting fact is that the dispersion measure law is close to the sort of classical alpha equals 2. So alpha equals 2 is true in the limit of a very undense plasma. As you get close to the plasma frequency, there's corrections to it. But some of the high signal-to-noise fast radio bursts have alpha very close to 2, which suggests that the dispersion is coming from a fairly low-density gas. Probably not a high-density gas that might be very near to the source of the radio burst. Also, the scattering width is too large for the dispersion to become the source. As those you that are familiar with lensing, it's best to have the lens halfway between you and the source. If it's very close to you or very close to the source, the amount of lens is much smaller, and you don't get the same amount of scattering. And scattering is basically a lensing. It's a different time of flight with different paths to view. So what's the population look like? Here's the dispersion measure versus number. So here's a curve of dispersion measure versus redshift from the intergalactic medium. Here's the law at low redshifts. You see that the number of events sort of cut off at about 1,000, which is about a redshift of 1, which is sort of strange. You wouldn't, the cosmological volume continues to increase as you go above a redshift of 1. And it's claimed by the observers that they'd be sensitive to things in higher dispersion measure. So it's sort of weird distribution, not quite what I'd expect. You can look at dispersion measure, which is a measure of distance, versus the signal to noise or the flux. There seems to be no good relationship. So it's not a good standard candle. And so that's sort of worrying. You expect the further ones to be dimmer and the closer ones to be brighter. That doesn't really seem to be true, except for the very high dispersion measurements. So these are things that people have to figure out. There's a claim in the literature that the flux distribution is not Euclidean, which would be alpha equals 1.5. So it's claimed by this group of people using parts data that alpha has to be less than 1, which would be a non-Euclidean slope. And since we know that this thing is not probing high redshifts where you expect non-Euclidean effects to come in, that's sort of unclear what's going on with that. Though Oppenheimer and Penn claim that the error bars are actually much larger than Euclidean is permitted. Another thing you might look at is the energy budget and the size. Like I said, the size should be less than about 1,000 kilometers for these fast regular. These nanoshots are basketball-sized things. These things have to be smaller than 1,000 kilometers by the causality argument. And also there's the energy. Their energy is about 10 to 38 ergs. So it's not the biggest energy you've ever heard of in astronomy. Supernova or compact binary coalescence releases like 10 to the 53 ergs in energy. So if that's the cause of this, it's a small fraction of the total budget. You could look at the energy in the magnetic field of a neutron star, convert all that to radio wave, that's 10 to the 45. So get it. It's within the energy budget of things that we know about. If you look at the rates, there's different ways of measuring parameterizing rates. So basically, the rate that people see at this fluence level is about 10 to the 4th per second per day. That corresponds to 1 every 1,000 years in the Milky Way galaxy. If you weight it by the number of stars, you compare that to the gamma ray bursts. All right, so the gamma ray bursts are much less frequent, so they can't be the same as gamma ray bursts, but we're pretty sure that gamma ray bursts are beamed, and so that it could be that the beaming angle for fast radio bursts is just greater than the same object. You can compare it to all core collapse supernova within the volume of the redshift range allowed, and the FRB rate is smaller than that. And the compact binary coalescence rate is fairly uncertain. There's certain people that have very strong ideas about what it should be, but the fast radio burst rate is about at the upper end of the allowed compact binary coalescence or neutron star coalescence rate. Of course, we'd expect LIGO to tell us what that is in the future. Another piece of evidence is sort of the duration, a millisecond. That we work in neutron star burning coalescence. That's a number that's familiar with you. Here's the millisecond time scale of various fast radio bursts. You see the same thing at the end of a chirp from a gravitational wave source, or from neutrino emission from a coalescing neutron star binary. So milliseconds is the time at which things happen when neutron stars coalesce. That's a longer time scale.
Now with the chirp is, you know,
Talking about the last
no, what I'm saying is increasing the signal, whereas the fast radio bursts like threads a lot.
They look like what?
Threads. That fast-wise expedition.
Well, I'll give you a rationale. What happens in the last few milliseconds of coalescence of like radio emission. Of course, you don't expect this. It's not like there's two plus and minus charges moving around
Right, but I mean, you're showing that, as you said, the chirp, you know, it's not really the chirp, it's something else, and it's something that doesn't have the fat-like characters that all those do.
Okay, well then there's the repeater. So here's an optical image of the repeater area. The repeater is identified through this little thing here. Here's a VLA observation of the radio source that's in that direction. The black points are this sort of non-burst, non-short time skip things, it's slightly variable. And the red diamonds are the fast radio bursts that the VLA detected. And so they're not terribly correlated, but there is this variable radio source here that seems to be in the same direction as the fast radio burst that we detected. And of course, the thing is that the VLA has much, much higher angular resolution than the Parkes telescope. Same with the optical images. It's even been looked at with VLBI observations. Here's the persistent radio source here. Here are a bunch of radio positions. Of course, you get to the milli-arcsecond angular scale, and you start having to jump around in various scintillation effects. But anyways, it's pretty clear that the fast radio bursts are very close to persistent radio source, very close to the optical source. And here's a plot of the spectrum versus frequency optical radio, sub-millimeter. So most of the observations are upper limits on this thing. And what they did was they plotted various other types of objects with their spectrum. So particularly the orangey pink one is the Kraft nebula. So the positive detections which are down here seem to match the Kraft nebula spectrum fairly well. So it might suggest it's like a lot of the illusion is like the illusion from the Kraft. So anyways, I don't know if that tells you what they are, but it tells you a lot more about them, at least this one particular one. So what good are they? Well, one thing is that the dispersion measures the IGM, which is the ionized baryon. Most of the ionized baryons in the universe, and that's otherwise nearly invisible for most observations. So if you just had a homogeneous universe, the dispersion measure versus redshift would follow this here, given by things to do with the dark energy, etc. So this is sort of cosmological distance redshift relationship, probably. But of course, what happens in practice is that the universe isn't exactly uniform, just like with weak lensing. Things are inhomogeneous. Here's sort of a cartoon plot of galaxies. The beam will pass through the galaxies and might clip the edge of the universe, or miss another one. So that leads to variations from this law. So, but one thing you could do independent of that is you could try to do, in principle, you could do a total baryonic inventory, since we have random lines of sight, which you see all the ionized gas. So that you could do. Of course, there are selection effects, which that's the way up. You could, by correlating the fast radio burst dispersion measure with whether they're galaxies near the line of sight, learn something about the outer edge of the gas and galaxies, or circumgalactic medium. So that would certainly be interesting. You could try to make a 3D or 2D map of the dispersion measure. You really need some sort of other redshift proxy to fill out this gas in the universe. Another thing which, of course, interests us at Fermilab is precision cosmological parameters. This is the Hubble diagram. And if you could get the redshift of all these fast radio bursts, and you believe this formula, you could measure the dark energy. This measurement dispersion redshift, and at some level, all these fluctuations should wash out. Figure out if you go to the atomic sky, just sort of supernova diagrams. So here's a simulation by Flynn et al. Of what the distribution of dispersion measure for object at a redshift 1, including the inhomogeneities. You get the black curve. it turns out it depends somewhat on the amount of feedback in galaxy star formation. So basically, if the galaxies are big and puffy, you get more variation. But you can see in an ideal case, the dispersion measure, the error in the dispersion measure distance might be 10% per object. And you get 1 million of these things here in principle if you try really, really hard. And this might allow you to have a better statistical handle on dark energy equation state than super. But I warn you to beware of refractive simulation. So here's this is actually a measurement of the Crab pulsar time versus frequency flux. It seems to vary with time, and this is due to some sort of plasma effect in the Crab pulsar area. Maybe something near the Crab pulsar that's causing caustics to happen. Things vary, and so here's a plot of some fast radio. You see structure in this, and you don't know whether the structure is due intrinsic to the source or whether it's due to some sort of simulation. And so actually, there's a lot of things that go on besides just the simple dispersion. There's magnification, and all these things have effects on the selection function. And how this shape looks like depends on how well will tell you how well you detect it. So there's all these complicated selection effects, and maybe the non-Euclidean slope of the counts have to do with that hasn't been taken account of. That's what a lot of people think. There's a paper recently by Nunez et al. Which suggested that you could look for machos by looking for like double features of fast radio bursts due to sort of microlensing. And the time scale for that is hundreds of microseconds to milliseconds for machos in the 30 solar mass range, which might ring a bell. You could, ideally by having these sorts of time sensitivities, 0.3 to 3 milliseconds, with a long period of fast radio bursts from each time array, you could rule out this parameter space of machos. But I would warn you that these things are probably not macho gravitational lensing events. I think a much more likely explanation is that they're plasma lensing effects. And so people are going to have to work that a lot. And so that's going to be a long process. So I'm running out of time. So there was this idea that these fast radio bursts were major life events in the neutron star, needing core collapse or contact matter coalescence, or maybe this delayed collapse. This quasar phenomenon, which is also called SIRL. But all these things are cataclysmic things. They wouldn't repeat, and if we take this repeating thing as being true, then probably this so all of these things that produce large numbers of neutrinos. So all these things produce huge numbers of neutrinos. They and also huge numbers of gravitational waves. They're sort of ruled out if all fast radio bursts repeat, because they only happen once in a lifetime. So I'm not going to go over, so I'm going to skip a lot of this stuff. But if it were true, you could measure neutrino masses this way fairly accurately. There's a curious, I will tell you a little story about neutrino masses. It's curious that the sensitivity neutrino mass from time of flight measurements is sort of independent of the distance per event. Because the size of the signal, because what you're measuring is the fact that the low energy neutrinos arrive later than the high energy neutrinos. And the amount at which they arrive later, compared to the intrinsic width of the burst, is actually proportional to the distance. So the further away, the bigger the signal is. The signal is also smaller because the number of neutrinos you take your detector from far away is less. But actually, the signal to noise for measuring neutrino masses from these sorts of kinematic arguments is independent of distance. So one in the galaxy from this method is just as good as one that I mentioned 10, as long as you get several neutrinos in your detector, which requires a very large detector. But anyways, if it turns out there are two classes of fast radio bursts, and one of them are these major neutron star-like events, it could be that in the future, if you build very large quantum strength-up detectors, you can measure the neutrino mass fairly accurately from kinematic considerations. So the reason why, so here I plotted two tails, and the two tails are actually the mass gap between the electron of unity neutrino and the tau neutrino, the mass gap. So anyways, that's an interesting idea. Let's get this. Big detectors. Military is thinking of building big neutrino detectors for reasons. For a similar thing, you could extend the reach of LIGO by using the time triggers from fast radio bursts. Look for, correlate the time trigger of the fast radio burst with the strain measurements of LIGO. And you could extend, a rough calculation, suggests that you could bring the signal to noise of a population that is equal to 0.7 neutron star coalescences down to a much smaller, signal to noise of a much smaller ratio. So you can extend the reach of LIGO if these fast radio bursts happen to be accompanied by large amounts of gravitational radiation, which is only true for cataclysmic scenarios, which may be ruled out. Here's a picture of seagulls and starlings. Anyways, the main point is that electrons that produce these very bright things act like starlings, not like seagulls. They all live together. The reason why you get very bright things is because the emission goes. It's the number of particles squared. Another thing to note is the electric field of the nanoshots is very close to the Schwinger limiting value. Here's some numbers. Talk about, here's the Schwinger pair production rate. You see it starts from a very small value, goes to a very high value. And remember, this is like 50 orders of magnitude here. So it's a very steep IV curve here. So once, for any astronomical object, once you cross 2 times 10 to the 12 Gauss electric field, you go from 0 Schwinger pair production to more than enough to short out the electric field you have. And there's a simulation of that. And you can use this sort of pair. So basically the idea is here's a space-time diagram. You have a large electric field, you produce charge here, the electrons go one way, the positons go another way. When the two balls of charge separate from this shorting up, and you get a large EMP. And that could be the source of the nanoshots. And my claim is that it could be that this nanosshot phenomenon is really the engine that drives all of this stuff. It drives the giant pulses, it could drive the fast radio bursts. What you need is higher time resolution. And the thing is that the plasma effects tend to smear out in a nanosecond structure here. But it could be that this sort of Schwinger pair production mechanism is an important thing that sort of gives you the electric field scale of the production of these electromagnetic pulses. So anyways, I was talking about nanoshots. What does that do with fast radio bursts? Well, if you take 2 neutron stars, and they have a magnetosphere, they have a magnetic field and a pair, electron-positron pair atmosphere that's produced spontaneously, and the atmosphere just sort of sits there to some extent, fairly quiescent. But when the two get close to each other, you start getting interaction of the 2 magnetospheres, and you get MHD dynamo, and the magnetic field strength grows by many, many orders of magnitude in a few milliseconds. So in these simulations, the magnetic field moves at 10 to 15 Gauss in less than 5 milliseconds. And if you just need a very small, so they did this using MHD, so in MHD, the electric field the relevant electric field is 0 for Schwinger pair production. You just need a few percent deviation from the MHD approximation to get Schwinger sparks going off all the time in this cloud. And this would be a rapid onset, keep a rapid onset. That wouldn't necessarily be a rapid turn on to a production of gigahertz radiation. But another thing that's going on is the Schwinger pair production is producing pairs, which effectively increases the opacity of the stuff around it. And it could be that the reason that the fast radio bursts turn off is because of increasing opacity. So anyways, that could be, in this cataclysmic scenario, that could be a way of producing a fast radio burst with the right time scale. Another thing to note is that, so I would argue that you can't make anything above this line, but else you would Schwinger parodies. No electric fields ever exist up here, the Schwinger effect. And that corresponds to an acceleration of particles in one cycle of up to eV energies. So basically in all of these things, this Schwinger spark is basically electron-positron collider. Occasionally the collide and annihilate and produce neutrinos. So you actually have a time-triggered source of PeV neutrinos, which might be of interest to some of us. Running a large block of ice photomultiplier. Okay, so that's my talk. So here's a thought about the future taken from China. So basically, this is a projection of the rates you'd expect of events per week from various detectors. This top one is China, which is actually going to come online in the mode that we want it in the next year or two. And they expect to see several events, 100 events per week. So we go to a situation where maybe there's 20 events published to 100 events a week. Now China won't have a good look, and this is independent of this log n log s. What it does depend on is that the spectral index frequency is such that there are a lot of bursts below 800 megahertz. You know there's at least one. We measured one in the Green Bank telescope. Presumably there are many. And so we're going to a regime where there's very few things to look at. There'll be lots. And probably some of them will repeat. So the fast radio burst scene will change a lot. So in summary, fast radio bursts are real. They're extreme astronomical radio burst phenomena. Until in 2013, most people doubted that. They're probably mostly at cosmological distances. At least one of them is. We'll learn more about that in the coming year. Unless they're multiple flavors, they're not self-destroying events like mergers. They increasingly seem to look like neutron star behavior that we've already seen, giant pulses or magnetar flares. There's only one fast radio burst we know a lot about, but like I said, that will change soon. They seem to be an excellent probe of cosmological ionized gas and also the surface like medium of galaxies. It's possible they could be used for precision cosmology, but I wouldn't bet on it. They may act like a PeV particle collider, like a time trigger, which might be a different way of doing collider physics than we used to. There's a decreasing likelihood that they're cataclysmic and that they are accompanied by large gravity wave or heavy neutrino emission. But of course, that's yet to be seen. If they were, that would be a real watershed, especially in the gravity wave community, because we are building gravity wave detectors. We're not building necessarily large in terms of water detectors, but larger than hypercane, which is really what you need. But anyways, things are about to change, and who knows what will find.
Thank you for a very stimulating talk. That was exceeded all expectations. Do we have some questions? Tom?
You
you argue against the cataclysmic scenario with the one repeater, why does the repeater and all the other bursts have to be the same phenomenon? They just happen to be at the same observable phase space.
Well, we know that gamma ray burst separate. Well, it's sort of the Occam's razor argument. I would have bet on coalescent star binary until the repeater comes. So maybe I'm just discouraged at this point.
Yeah. You have some interesting comments or questions?
Well, I just, it's a different kind of one, but.
Should we give you the microphone or you?
Yes. No, well, so what is the evidence that you could make why there's definitely not ultra-relativistic behavior going on?
So why aren't they like gamma ray bursts? Is that your
Well,
question?
so.
Why isn't it
Well,
just
I mean, they
narrow?
have enormously high brightness temperature. But if you can get around some of the size problems, for sure, if they're ultra-relativistic. So what's the argument against that?
Well, I think a lot of people that try to make models of this, they run into things like there's a lot of gas around your thing and the free self-absorption and going radio waves. So in other words, there'd be this is true of a lot of models that in things where there's a lot of gas around, it's difficult to get the radio waves out. So people generally think that radio waves come later in any of these sorts of scenarios. But that doesn't preclude the fact that it's a unique phenomena. But I think we have to find the context in which to do that. People
I
have
think
to
there's a relative jet that could go out and the emission could come from somewhere away from us.
Right. So I mean, I guess in gamma ray bursts, they think a lot of the emission comes from different shells banging into each other. Is that correct?
But very far away from collapsed objects.
Right. But you have to be sort of on the outer edge of all of that for the radio waves to come. But anyways, what the thing to do now is to figure out ways to test like this. Come up with a scenario and figure out how you can tell it from something else.
Craig?
So the cosmological radioactive medium, if you really get so many objects, that looks like it's going to be pretty easy. I mean, what's going to be awesome? That's where most of the variables are.
Say it again. I mean, the problem with getting lots of events is to build the hardware to do it.
But China's going to have said they're going to do that in a few years.
Well, they're going to get 100, but they're not going to be localized, so you're not going to have any redshifts.
Right. So that's the main obstacle is getting the.
Well, what actually, this is an easy problem to solve. What China needs to do is build outrigger radio telescopes. They're maybe 10 kilometers away. They don't have money to do that, but if they did that, they could localize it so that you could then
get the angles.
get where it is. And then if you had like a pre-existing galaxy redshift catalog, you could say, oh, it's that galaxy there, and that's a redshift 0.35. So it can be done. People that work at, like the Australian people, that one guy, Mark Park, gave a talk about this, and he had a hard time thinking you could go much beyond what Parks does now, or what China is going to. If you put effort into this, you can do a lot. You can do almost all of them on the sky if you really wanted to.
Dan?
I wondered if the repeating bursts could be quasi-catastrophic in the sense that maybe you have, I wonder what the energy in both those bursts is. Could you have asteroids hitting a neutron star?
Well, the original asteroids hitting a neutron star, people were thinking that was in the galaxy. Joe Silk actually tried to get me to think about this, because there's some guy in Paris that works on it, and I'm having a hard time understanding where the millisecond comes from. These asteroids would be torn apart when they're very far away from the neutron star. I think the time scale would be much longer.
Okay, so now you get to hard questions. We're going to leave you with the students for a few minutes. So the students should move down front.